So, today is the third lecture in a series of 5 lectures on general relativity. Once again, this is Sukant Bose. This time I am going to talk about the stress energy momentum tensor of fluids. We will do some examples that are very close to being realistic, but also allow us to solve Einstein's equations, which I am going to talk about subsequently. So far we have introduced the Einstein tensor, which is one of the tensors that describes the curvature of space-time. But this curvature is affected by the distribution of fluids, and fluids are described by the stress tensor. So, that is the motivation then to talk about stress tensors. But we back up a bit. For continuity, I remind you that one of the quantities we introduced in the last lecture was the Riemann curvature tensor, which is this rank 4 tensor. All of these 4 indices take 4 space-time coordinate values each. When you contract the first and the third of these 4 indices with the inverse of the metric, you get this rank 2 tensor whose components are r, mu, nu, and these are the components of what is known as the Ricci tensor. Variously you will see some authors describe components of the Ricci tensor with these 2 indices both as superscripts. We know how to raise these indices or lower these indices by the action of the inverse metric or the metric itself. The Ricci scalar, which is invariant under coordinate transformations, is obtained by another contraction. So, this time you apply the inverse metric on the Ricci tensor. Finally, the Einstein tensor is obtained by this combination of the Ricci tensor and the Ricci scalar. The nice thing about this tensor, the Einstein tensor, is that it is divergence free, and this comes from the Bianchi identities, which we had talked about last time. The Bianchi identity can be written in terms of this combination of the covariant derivatives of Riemann tensors. So, with this we transit to describing certain preliminaries that will help us in understanding the stress energy momentum tensor of fluids. One of the things that will be useful is to revisit what the 4 velocity vector is of a particle, in this case a massive particle. We use the letter boldfaced u to define this vector, and this vector is nothing but the proper time derivative of the position vector x. So, in an arbitrary inertial frame, the components of this 4 velocity vector can be expanded in terms of the proper time derivatives of the coordinates that describe the position of the particle. So, this would be the time coordinate x 0 and the 3 spatial coordinates x 1, x 2 and x 3. Now, if you go into the proper frame of the particle, even if it is locally inertial and not globally, and let us say we continue to call it the prime frame, the S prime frame, then the time as measured in this S prime coordinate by the particle itself, so by the particle's clock, is just the proper time by definition, as you must have learned in special relativity. So, in such a case, the components of its 4 velocity vector in this preferred frame from the perspective of the moving particle, namely the S prime frame. So, the frame that is moving with the particle, which is the frame that is moving with the particle, okay, that is the proper frame. So, in that frame, the particle does not change its position, namely x prime, y prime, z prime, are fixed. It's just that its clock keeps ticking away. So, t prime keeps advancing, but t prime is the same as tau. So, the derivative of t prime with respect to the proper time is simply unity. The other derivatives are zeros. So, these are then the components of its 4 velocity vector in its very favorite frame, in its proper frame. So, 1, 0, 0, 0. The same velocity vector, when its components are examined from a different frame, which we call the S frame, and that has something I have been calling the lab frame or the classroom frame, then because the particle is traveling with respect to S, it has a boost given by the Lorentz factor gamma. So, that tells us that the time coordinate of this frame S is just gamma times the proper time. Okay. In such a situation, the components of the 4 velocity vector are just again dx by d tau, but then x, the 4 position vector in S, has components t, x, y, z, and therefore, the proper time derivatives of these quantities will now all have the Lorentz factor gamma, and that is because dt by d tau is gamma. So, you can use the chain rule to flesh out the proper time derivative of the spatial coordinates and express them in terms of the ordinary derivatives dx by dt, dy by dt, and dz by dt. But that then brings this prefactor of dt by d tau in all of them, which is nothing but gamma. So, that is why you see the presence of gamma in all of these components of big U. The others Vx, Vy, Vz are just dx by dt, dy by dt, and dz by dt. So, this is going to be useful, as you will see in a moment, in defining the stress energy tensor, for example, of a collection of dust particles, which are doing nothing, let us say, but just sitting in a tray below a chalkboard, right. And a tray and these dust particles, let us say, are static with respect to you in the classroom. The other vector that is going to be useful is the number flux 4 vector. So, we go back to that example of the dust particles, right, and another component in the definition of the dust particles is that these are non-interacting, they are not colliding with each other, they do not exert forces, even if electromagnetic forces or gravitational forces on each other. For simplicity, we require one more thing, which is not essential as such, but let us say all of these particles have the same rest mass m. Then the number density n in the proper frame of these particles, which is the S prime frame, can be useful to define another 4 vector, and that is as follows. These particles each have a 4 velocity u, like this single particle we just illustrated earlier. So, we can go on to define a new 4 vector in which in the S prime frame has the following components. The first component is the number density vector, sorry, the number density of these particles n, in this case in the proper frame, and let us say the other 3 components, the spatial components of this new vector are all zeros. We label this what will be known as the number flux vector. Okay. But if you examine the components of the same vector, which we call the number flux vector, from the perspective of the classroom frame S, then all of these particles will be moving in that frame. They will all be boosted, right, with a velocity magnitude of v. And owing to Lorentz contraction, the number density will be affected as well, and that is because if, for example, S prime were moving in the x direction, then the box carrying those particles will be contracted along the x direction by a factor gamma, and that will increase the number density to n times gamma. So, that is why it is not a surprise that as viewed from the classroom frame S, this number flux vector has a 0th component, the time component, which is gamma times n, because that is the number density as observed in S. Remember, the particles are moving with respect to S, and their instantaneous proper frame is the S prime frame. And this, these particles will now appear to move along the x-axis, and that is because S prime itself is moving along the x-axis, right. So, if that were the only motion that these particles had, then even the x component will be non-zero, and one can show that the flux of particles through an x equal to constant surface would just be n times gamma times Vx. So, but suppose we deal with a general case where these particles are moving in some arbitrary direction with certain non-zero components along x, y, and z coordinates, right. And if that ordinary velocity components are Vx, Vy, Vz, like we discussed for this single particle case earlier, then the number flux vector will have all of these components non-zero. So, you will notice that this vector therefore can be just re-expressed as the number density in the proper frame, small n, times the 4 velocity vector u. You can establish that by comparing this expression for the components with this expression for the components of the 4 velocity vector. This will turn out to be handy, and indeed this is very much in the same spirit as we saw for the components of the 4 momentum vector, right, in the classroom frame for a bunch of particles that are boosted with velocity v in some arbitrary direction, okay, where v is the magnitude of the velocity. So, that will be equal to square root of Vx square plus Vy square plus Vz square. So, that is the spatial velocity part, the ordinary velocity. So, the 4 momentum indeed is also just the rest mass of these particles times the 4 velocity vector u. This prepares us well enough to deal with new tensor, which will be the stress tensor for the same dust particles. So, how do we define it? We define this tensor through an operation that is actually quite handy to produce new tensors from old simpler ones. So, we have two vectors, namely the momentum vector and the number flux vector. If you define a certain type of product operation, which will be made explicit in a moment, we call this the tensor product. Then you create from these 1-0 tensors each a new tensor that is a 2-0 tensor. So, the way this operation is defined is that the scalars m and n can be factored out, so that the tensor product operates only on the tensor arguments, namely u and u in this case. Each of these u's is taken from p and n respectively, as we saw on the previous slide. P and n both are just some scalars m and n respectively multiplied with this 1-0 tensor, which we call the 4 velocity vector u. Now, n times m, namely the number density multiplied with the rest mass, is nothing but the rest mass density, right. If you were to expand this to involve energy, so replace m with the rest energy of a particle, which of course is just the rest mass, then this would be the rest energy density. Now, the components of this tensor are the energy and momentum fluxes across various 3-dimensional surfaces, and I am going to detail this in a moment. So, let us understand the operation of T a little better. We know that vectors such as u were defined as 1-0 tensors that acted on the dual basis vectors to produce scalars. Or more generally, a 1-0 tensor acts or is a map from a dual vector to a scalar, right. So, of course, all dual vectors can be expanded in terms of the basis vectors. So, which is why T, this 2, 0 tensor, is defined as a map from two dual vectors, omega alpha and omega beta, both with tildes, producing a scalar. So, what is the scalar? We can understand that in the following process, which also helps us understand the role of this tensor product. So, T is just rho u tensor product u. So, that is what I have written here, and this object has to operate on two dual basis vectors, and the tensor product is defined in such a way that its arguments operate in the given order on the basis dual vectors. So, the first u operates on the first basis dual vector u alpha, and the second u acts on the second basis dual vector. Now, in this case, since this is a symmetric tensor, you have it defined in terms of u tensor product with itself. The order ultimately does not affect the answer, but you can imagine another tensor which is produced out of two different tensors and not the same ones, in which case, of course, the order in which you act will make a difference to the answer in general. So, and that is especially true if, for example, we are dealing with antisymmetric tensors, because that can result in the change of sign, okay. And a mixed tensor will have non-zero antisymmetric tensors in them, and therefore affect the final answer, depending on which order in which you bring in the action on these basis dual vectors. In this simple case, the action of u on the basis dual vector is just the component of u. So, in this case, u alpha first and then u beta next. So, this is then the component of the stress tensor for the dust particles that we just described. In frame S prime, which is the proper frame for that collection of dust particles, only one component of this stress tensor is non-trivial, which is, of course, T 0 prime 0 prime. The prime denotes the fact that you are taking this the time component, the time component in the S prime frame, and it is only this component that is non-zero, because it is only u 0 prime that is non-zero, as we saw in the previous slide. The spatial components are 0 because the particle is not moving with respect to S prime. Its spatial coordinates are not changing with respect to S prime. So, so only u alpha and u beta in this prime frame are non-zero, and they are both equal to 1. That is because d prime is just d tau. So, d t prime by d tau is unity. So, that leaves you with just this proper energy density as the surviving component. All other components in this big matrix are 0. How big is this matrix? Well, each of these indices can take 4 values, so 16 in general, but as an assignment I will ask you to show that this tensor, the stress energy tensor, for a perfect fluid at least, is symmetric. So, for dust is a special example of a perfect fluid, and in this case it is manifestly symmetric under the interchange of alpha and beta, but this symmetry property extends to more general fluids than just dust. In the frame S, things become more interesting, and that is because in that frame U has non-zero spatial components, because these particles have non-zero velocity components Vx, Vy, Vz. So, therefore, T00 itself is just rho u0 u0, but each of these u0s, time component of the 4 velocity vector, is the Lorentz factor gamma. So, you have 2 of them from the 2 u0s, and so this is indeed the boosted energy density, rho times gamma square. One of these gammas comes from the fact that the energy itself is the 0th component of a 4 momentum vector, and the boost changes that by gamma. And the second gamma comes from the fact that the number density is also getting affected. It is increasing because one of the length dimensions is contracting by a factor gamma. So, you understand the source behind these 2 gamma factors. So, it is easy to remember this and even check that this is correct. Another type of component will be the time space component. Here k's and j's are spatial components. So, T0k, going back to this manifest expression for the dust tensor, is just rho times u0 times uk. U0 is gamma, as we saw before, and uk is just gamma times Vk. So, together you have rho times gamma squared times Vk. This is the energy flux. Energy comes from the first coordinate, which is the time coordinate. So, it is the energy flux across xk equal to constant surface, where this second index k comes from the fact it is a flux in that direction comes from the second index k here. Tk0 is the same thing ultimately, but it is interpreted differently because the first index is now a spatial index. So, this is the k momentum density, just like T00 will be the T momentum density, but T momentum is nothing but energy. So, it is the energy density. And finally, you have terms that look like Tjk, and that is just rho times uj times uk. Each of these spatial components of the u's will bring gamma times the component of the v's. So, you get rho times v square vj times vk. This is, can you guess this? This is the flux of the jth component of the momentum across the xk equal to constant surface. So, when the kth, when you are dealing with the kth momentum cutting across the xk equal to constant surface, you have a very special type of component tkk. These are the diagonal spatial components, and these are nothing but the what we call the pressure of the fluid. So, I already gave you an assignment when I asked you to prove that the stress tensor is symmetric under the interchange of its two arguments. The second thing I would ask you to prove is that this tensor is conserved, namely it is divergence free. Stated in a different way, in component form, it is that the covariant derivative of T alpha beta with beta contracted is equal to 0. This should be reminiscent of the divergence free nature of the Einstein tensor, right, where we showed that G alpha beta covariant derivative with respect to x beta vanishes, and which already motivates a similarity of sorts between G alpha beta, the Einstein tensor, and T alpha beta, the stress tensor components. So, moving on with some more description of stress tensors, let us consider the example of a perfect fluid. So, the way we define a perfect fluid is that in an inertial frame that is locally at rest relative to the fluid element of interest, which is maybe some small piece of this fluid distribution, then a perfect fluid is one that has no viscosity and no heat conduction across any of the surfaces of that fluid element. So, with this definition in mind, I would ask you to reason that the components of the stress tensor can be written as follows, namely that in the special frame it is all diagonal. Of course, if you made a boost, then these components can get mixed up, but still continue to define the perfect fluid if you started with this diagonal form in the proper frame, right. So, T00 remains the energy density rho, and the non-zero components, the other non-zero components in the proper frame are all diagonal. In this case, the remaining spatial components, the TKKs for k equal to 1, 2, 3, or x, y, and z, and they are all pressure. In this situation, you can argue that no direction will be picked up as different from the others. So, the pressure has to be the same in all directions, which is why all of those TKK components are equal to each other. From the context, I would ask you to be able to tell which P means what. I know it is getting confusing. I mean, already it seems that P is one of the favorite letters for special relativists or general relativists, relativists in general, but you can tell it from the context. In this case, when we are talking about fluids, P and we are not confining ourselves to just say an atom in the fluid or a particle in the fluid, then P will denote the pressure. But also notice that when we use P as a 4 momentum vector, we will use it as a bold faced letter signifying the fact that it is actually a vector. And the third context in which we used P was to describe a general dual basis vector. Oh, not a basis vector, just a dual vector. But I will be careful in pointing out what I mean by a specific P in most cases. So, let us go through a few examples of stress energy tensors. Since we just finished discussing dust, we realized that in the proper frame of the dust particles, the only surviving component, what we call the T0 prime 0 prime component, was the energy density. All other components of that stress tensor are 0. So, you have a situation where in the proper frame, and now in this case I am dropping the primes. So, in that kind of a situation for dust, all the pressure vanishes, there is no interaction, right. So, the equation of state of dust is P is equal to 0. Of course, you cannot have energy density equal to 0, and that is because in that case you will have a trivial situation where your fluid has no energy density nor pressure, which actually is the case for vacuum. So, vacuum has all of the components of T alpha beta equal to 0 identically in any frame. The second example of fluid is radiation for us, and you already studied in electrodynamics by examining the Poynting vector of radiation that the pressure imparted by radiation on the surface it impinges is 1/3 times the energy density. And so, that is actually the equation of state of radiation. This is indeed a relativistic equation of state, because the photons are traveling at the speed of course, light. Dark energy, which has been in vogue for about a couple of decades, ever since the cosmic microwave background radiation found the omega lambda. So, the density parameter in lambda to be non-zero, where lambda is cosmological constant, and ever since the high redshift supernovae experiments also indicated the same thing. We of course are then required to come up with the stress energy tensor for dark energy, and this is an entity which is repulsive in nature, unlike gravity, which can only be attractive. In the case of dark energy, which we invoke to explain the accelerated nature of the universe's expansion, you indeed have a situation where for any non-exotic matter which has a positive energy density, the pressure imparted by it causes this accelerated expansion. So, the pressure is then negative of the energy density. Some of these examples will be handy later on. So, with that preparation and introduction to stress energy tensor, we come back to what could be the equation that defines how gravity, or in Einstein's case curvature of space-time, is influenced by fluid distribution. So, one of the key insights into this equation came from the principle of equivalence. I described an exposition of it in the last lecture, but did not give it this name. This happened when I was describing how you can get into the same freely falling frame of group of 4 balls that were falling under the gravitational influence of Earth, and I showed you how momentarily you can get into a frame that is at relative rest with respect to these balls. So, you are in their momentarily co-moving rest frame, and in that situation you will not be able to tell whether you're accelerating or you're just responding to Earth's gravity. So, the principle of equivalence technically in its weak form states that you can hide the effect of gravity by getting into an accelerating frame. There are other versions of equivalence which I would urge you to read up, like the strong equivalence principle or even Einstein's equivalence principle. One of them states, for practical purposes in our equations, you can it is equivalent to replace the covariant derivative or the semicolon nu with the ordinary derivative comma nu locally. That is, you can always go into a local frame where the crystal symbol vanishes. Very good. So, the principle of equivalence, I should say, was key in Einstein realizing that gravity is but space-time curvature caused by the presence of stress, energy, momentum distribution, for example, matter, radiation, etc. So, the space-time is curved because in our neighborhood, primarily because of the sun, and if we are all falling towards the sun, the curvature doesn't care what we are made of, whether we are made of lead or carbon mostly or water, we are all going to fall the same way, because we are just we are trying to move along the straightest paths possible in this curved manifold, right. So, that is another manifestation of the principle of equivalence. But what curvature quantity can be made proportional to 2 alpha beta? Because we want to come up with a situation where curvature is responding to the presence of fluid as quantified by the stress tensor components T alpha beta, right. Of course, it has to have the correct weak field non-relativistic limit. So, in other words, that limit should be Newtonian gravity, given how successful Newtonian gravity has been in understanding the motion of massive objects like planets orbiting the sun, right. But also if T alpha beta is divergence free, then that curvature quantity should also be divergence free. So, now you are already getting a hint as to where I am going from here. One can show that the Ricci tensor, which is again rank 2 tensor like T alpha beta, prima facie might be a candidate for that curvature quantity that is made proportional to T alpha beta, but this is not divergence free. So, that is, and since it is not divergence free, it imposes strong restrictions on T alpha beta, which can preclude realistic matter of certain types. But we do not want to do that, because such matter is present and we want to understand their effect in the way they have gravity about them. So, but this is why in our preparation we introduced the Einstein tensor, and so one can make an attempt by saying that, okay, what about, let us make Einstein tensor proportional to the stress tensor. Now, in this version of that proportionality, I have chosen to lower both of these sets of indices on the Einstein tensor and the stress tensor, and nothing changes. If you prefer raising these indices, then you can do that consistently by applying the inverse metric twice on both sides. Okay. Now, the proportionality factor here is something I have just taken out of the hat, like a magician takes out a rabbit, but that is fine. There is another lecture that will be given by one of my colleagues who will explore this Newtonian limit that I talk about of this equation, and when he does that, you will find that this proportionality factor has to be exactly this, so that the predictions of this equation, Einstein's equations of gravity, are consistent with the predictions of Newton's law of gravity in the weak field non-relativistic limit. This proportionality factor is simply 8 pi times Newton's gravitational constant big G divided by the 4th power of speed of light in vacuum. So, because G is very small and C to the 4 is very large, but it is in the numerator, this coupling factor is very small, and that is why it takes a lot of matter like the earth itself to produce any palpable amount of gravity. notice that gravitational force is easily withstood by the electromagnetic forces in the floor on which you're sitting or standing. If you want to flesh this out, you realize that okay, g mu nu is just r mu nu minus half small g mu nu times the Ricci scalar, and in this case the right hand side is left unchanged. So for a prescription for how to solve these equations to find how the space-time is around your object of interest, you go back to saying okay, you have some space-time. It could be spherically symmetric or it could be not spherically symmetric. We will start with some simple cases because symmetry helps in reducing the number of non-zero components of our tensors, as you got a hint of earlier. So if you have a spherically symmetric space-time, then the metric or the line element that tells you the physical distance between any two space-time events in that vicinity, right, then that will have a certain simplification. But once you know what the general metric is that describes spherically symmetric spacetimes, you can construct the Riemann tensor from it by constructing its Christoffel symbol and then taking derivatives of it. And then a contraction of the Riemann tensor will give you a Ricci tensor. Its further contraction with the inverted metric will give you the Ricci scalar. So this is how you are able to relate double derivatives of the metric components to the components of the stress energy tensor of your matter of interest, like dust or radiation, dark energy, or something more fancy. But once you solve, and there are multiple equations here. I mean, mu and nu are both spanning over 4 values of space-time indices. So 4 times 4, there could be 16 of them, but then you already know that r mu nu is symmetric, t mu nu is symmetric, small g mu nu is symmetric. So in 4 space-time dimensions, there are only 10 independent equations that you have to solve. Yes, 10 is a handful, but if you have additional symmetries, those equations, the number of them will that are independent will reduce. So if they don't, then you still have recourse to a numerical way of solving these equations. So spherical symmetry. So this is the case we are going to illustrate. This is indeed something that helps in reducing the number of independent components of the metric. Another symmetry that you will encounter, or you may have already seen, is something that is used to understand our cosmos, and that is the symmetry arising from the cosmological principle, which says that our universe is homogeneous and isotropic. So homogeneity, well, isotropy means that the universe looks the same no matter in which direction you see at a given scale, and homogeneity means that you have translational invariance. So you go from one point in space-time to another point in space-time, and the universe around you looks the same. Again, these refer to certain scales. Clearly the universe doesn't look the same whether you're sitting at this desk or walking away in the classroom where you don't have a desk. Okay, you don't have something as material as the desk. You have something more vacuous. I mean, for example, the tenuous atmosphere around you, right? So at these small scales, clearly the universe is not homogeneous or isotropic, but at scales of the order of 100 megaparsecs or so, where a parsec is is 3.26 light years, a megaparsec would be 3.26 million light years. So at those kind of length scales, to the best of our ability that we can tell, the universe is homogeneous and isotropic, and that essentially means that the metric components have they don't vary from one point in space to another point in space. So their spatial derivatives are all zeros. So that again is a big simplification of the Einstein's equations, and it allows us to study the implications of those equations of gravity on the fate of the universe. Namely, if you have a certain distribution of fluid in your universe, for example, at some point in time in the past, the universe was dominated by a cosmological constant. So then you use the type of equation of state I showed for dark energy and study how the metric components change with time. They don't change across space because of the cosmological principle, but they can still evolve with time, and you come across what are known as the Friedmann-Robertson-Walker solutions. So I've described this verbally. I won't have time to go into the details of this in a more technical fashion, but it's a simple example that you should work out yourself, maybe after you gain some experience with what I'm going to show here with spherically symmetric and static spacetimes. So spherically symmetric means that at every point in space and time you have this symmetry. So in other words, at any given, so let's say you choose some origin for your coordinate system. So you have the radial coordinate increasing in value going away from that origin of your coordinate system. Time keeps advancing forward, of course, but you can then imagine, because of spherical symmetry, populating your space at any given time slice with spheres with increasing radii, right? So when you do that, you know that on every 2 sphere the metric has to be of this kind, d omega 2, where d omega square is just d theta square plus sine square theta d phi square. Theta is the polar angle going from the north pole value of theta equal to 0 to the south pole value of theta equal to pi, and phi is the azimuthal angle that goes from 0 to 2 pi, right. So spherical symmetry, it doesn't matter where you choose to set phi equal to 0, but once you have set it, you go around a value of 2 pi radians, and in every direction the space-time looks the same. But the component of dr can be something different. Oh, by the way, and the surface area of each of these concentric spheres has to be 4 pi r square in flat space-time. So that then tells you that the coefficient here for d omega square should be like r square. And then you have dt square with g00, which again can be at the moment anything, because in general this quantity can be influenced by what kind of matter you have in your space-time. And so the other quantity that is non-trivial potentially is the cross term dt dr, and in the expansion g mu nu dx mu dx nu, this dt dr term will appear twice, because there will be a second time when you will have a dr dt term, but because of the symmetric nature of your space-time, g0r has to be the same as gr0. So you pick up a factor of 2 because there are 2 types of these. However, if you require your space-time to be static, that is, if you wait for some time and let the space-time to evolve forward in time, staticity means that if you were to now reverse and play that recording or tape backwards, you should see no change. But playing it backwards essentially means switching the sign of dt to negative dt, and if nothing is going to change either way, then this quantity has to essentially cancel out, so or not be present. So under spherical symmetry and staticity, this is the most general form of your metric, albeit in coordinate system that is nicely adapted to spherical symmetry. So you have a tt component of the metric, radial component of the metric, and then the 2 sphere. Now g00, because any separation along the time-like axis has to be time-like separated, as we saw in special relativity, this coefficient has to be negative. So that's why let me explicitly give a negative sign here and then bring in a positive factor e to the 2 phi. Similarly for gr, this has to be positive. All points along dr have to be space-like separated. So e to the 2 lambda is another positive factor, but phi and lambda in general can be different, again determined by the distribution of your fluid. But nothing in our consideration so far disallows the possibility of phi and lambda to depend on the radial coordinate. They cannot depend on the time coordinate, because staticity further implies that none of the metric components can be time dependent. So, what implications do we then bring forth to the Einstein's equations? What you do next is you take the metric components you saw earlier, where g time or g00 small g was non-trivial, g r was non-trivial, and then g theta theta and g phi phi for the metric components were also non-trivial. So, you use those metric components, and of course, you are using a special coordinate system here, and that is fine, that is allowed. You should do that. In fact, you should try to identify, given the geometry under consideration, find the best coordinate system in which the equations of Einstein's simplify the most, and because that then makes it easy to solve them and also makes your calculations less error prone. So, in these what in flat spacetime would be spherical polar coordinate system with an additional time coordinate, right. So, but now generalized to the possibility that the time and radial pieces can be different from unity, right. So, when you use that metric and its derivatives and construct crystal symbols from them, and finally work out the Einstein tensor components, then you can take this again as classwork or homework and show that these are the only non-zero components that will crop out of your work. So, the time piece of the Einstein tensor will be defined in terms of course, e to the 2 phi, which is just negative g00, you will remember, again small g for the metric, and it also depends on e to the 2 lambda, where that quantity is just grr, again with small g, but this Einstein tensor component depends on the radial derivative of that quantity. You can expect to have nothing but radial derivatives here, because the spacetime is static. So, moving on, similarly GRT will be found to depend on both lambda and phi, but this time it depends on phi through a radial derivative of phi. So, phi prime is defined as the derivative of phi. Actually, this is a typo, this should be r. So, this should be d phi by dr, r being the radial coordinate. G theta theta is expressed in terms of not just a single derivative of phi, but single derivative of lambda here and there, but also the double derivative of the time component of the metric through phi. Spherical symmetry then tells you that g phi phi is readily extracted from g theta theta by just this multiplication with sine square theta. So, prime is already defined, but if you see an over dot, then unless otherwise specified, it will denote the time derivative of the quantity on which you see that dot. We solve Einstein's equations in this first case for spherical symmetric static spacetime, but in vacuum. Okay. Does this have a physical relevance? Yes. The spacetime around the sun is mostly vacuum. If you think it is exactly vacuum, that is not true, because the solar wind is a collection of particles which, although very tenuous, does not leave the space around it as totally vacuum, but it is a vacuum to a good approximation. So, in that sense, you can expect the motion of satellites around the sun, okay, in this case planets are its satellites, right, to be determined by a geometry that we obtain by solving Einstein's equations for spherical symmetry and staticity in vacuum. So, vacuum means that T mu nu, that is all components of the stress energy momentum tensor, okay, also called the stress tensor for short, are all 0, right. If they are all 0, then all of the components, okay, interesting components of the Einstein tensor should be equated to 0. So, we start with the first two, GTT and GRT, that we met with on the previous page. You set them to 0. So, this gives you two first order differential equations with in two variables, phi and lambda. Indeed, you can show that this following choice, e to the 2 phi equal to 1 minus 2 m over r, where m is a constant, okay, and this in turn equal to e to the negative 2 over lambda, sorry, negative 2 lambda, right. This actually satisfies these equations. Furthermore, they also satisfy g theta theta equal to 0 and g phi phi, therefore, g phi phi equal to 0. So, this solution for phi and lambda, when inserted back into the expression for the metric in those coordinates that we will now call the Schwarzschild coordinates, gives you this form. So, this is the metric under the stated assumptions. So, the time component is minus in parentheses 1 minus 2 m over r, and the space component is 1 over 1 minus 2 m over r. Here m can be interpreted as the mass of the star, like the sun, around which in vacuum you are examining how physical distances can be computed from coordinate separations like dt, dr by using this metric. Okay. So, G mu nu maps these coordinate separations dt, dr, d theta, d phi into physical distances ds square. Of course, these are all infinitesimal, but if you can integrate for larger separations, then you will get larger physical distances. This metric is also known as the Schwarzschild metric, and using it you can verify which Einstein did, namely that Mercury's perihelion indeed precesses about 43 arc seconds every century, and that amount is determined by how far Mercury is and the mass of the sun. You can also calculate how much starlight will bend as these rays from faraway stars pass through the vicinity of the sun. So, once again, there is an impact factor that determines that, and also the mass of the sun itself. With that, we end this third lecture. Next up will be other interesting cases, such as a non-vacuum spacetime, and when we have a spacetime that has fluid in it, obviously we will have to ask what kind of equation of state is used to describe that fluid. Can we create realistic stars out of those? What about our own sun? We examined the spacetime around the sun, but what about the spacetime in the interior of the sun? So, these are the type of questions that we will bring up in the next lecture. Thank you.